Hi, my name is Sudarshan, and I'm a graduate student at the University of Central Florida. And today I'll be presenting on a work that myself and Dr. Sumati Patnaik did, which is reference-based color transfer for medical volume rendering. So the main motivation for this work was that in traditional volume rendering techniques, one essential step is to design proper transfer functions where a user interacts with a volume renderer by modifying the values in the transfer function. And he does that in order to obtain the best color and opacity parameters in the final rendered volume. So this work can be tedious and time consuming. And another reason to do this project is that medical images like X-rays, CT scans, MRIs are a valuable diagnostic tool, and they contain a significant amount of anatomical information for clinical procedures. So a colored image, however, could provide better anatomical information than an ordinary monochromatic image. So the objective here is to automatically colorize medical images such as MRI and CT scans and perform volume rendering with those colored images. So basically in our approach, first of all, we perform reference-based colorization, where color is transferred from a reference image to a target grayscale image. So when we perform colorization of a stack of grayscale MRI images with the help of a set of colored reference images, we obtain the colorized version of those MRI images. Then we use a direct volume rendering technique like GPU-based raycasting to render the colored 3D volume. With our approach, we successfully perform colored medical volume visualization, and essentially we eliminate the painstaking process of a user interacting with a transfer function to obtain the color parameters for volume rendering. So the diagram here shows the overall process. First, we perform reference-based automatic colorization of a stack of 2D MRI images. Do that to obtain a colored version of that stack. And then we perform volume visualization using those colored images. So the entire set of images that we use comes from the visible human dataset. Specifically, we use 33 MRI images of head and 328 CT scans of thorax and abdomen as our monochromatic medical image stack, which are also our target images. And we use 696 color cryosections from the visible human male, which are also our reference images. So the entire process can be divided into two parts. First one is the reference-based color transfer, and second part is the direct volume rendering with raycasting. The first part has briefly four components, and there are deep image analysis, colorization using guided image filters, gamma correction, and finally reference image retrieval. And in the second part, we have direct volume rendering. I'll briefly explain what was done on the first part, and then we'll move on to the volume rendering part. So let's look at deep image analogy first. So in the original pipeline of the deep image analogy paper, which was performed by Lau et al., it performs three major steps. First, it computes features of two input images, let's say A and B prime, at different layers of a pre-trained VGG19 network. And then on the second step, it uses those features to find deep correspondence between those images. Essentially, it uses patch matching algorithm in feature domain rather than in image domain to obtain the similarity mapping function phi between those two images. And in the third step, they basically perform reconstruction of images A prime, which in ideal case is semantically similar to A, but has the visual attributes of B prime. Here, the images are from the paper itself. We can see two images, A two of the input images, A and B prime, and the reconstructed outputs, which are A prime and B. So now for the color transfer problem that we have, we use a similar technique. First, we have two images. One is the target image, which is a grayscale CT scan or a MRI image, and another is a reference image R, from where we need to extract the color and apply it to our target image T. In the original deep image analogy paper, both of their input images are colored RGB images, but in our case, one of the image is a grayscale image. So first, what we did is that we took the luminance channel out of both of those images and performed deep image analogy to find the similarity mapping function phi. And then in the next stage, the similarity mapping function that we obtain from here, that is applied to the reference image R to get the final reconstructed image T prime. Now, ideally, T prime or T prime LAB should be semantically similar to T and contain the visual attributes of R. So we obtained the reconstructed output, but that was not what we wanted. So the process not only transferred the color from the given reference image, it also resulted in a transfer of a lot of other visual attributes like texture and style, which is not what we needed in our final image. So to solve this issue, we had to use guided image-based filtering technique to remove the unwanted distortions from our final image. So now we will move on to colorization with guided image filters. So as I said, the goal here was to only preserve the color and disregard the other visual attributes. So to achieve our goal, we had to perform some cross-processing with edge-aware guided image filters to obtain the final color image. Guided image filters are basically edge-aware smoothing filters, which preserves the edges but smooths out flat regions in an image. One such example of a guided image filter is the fast global smoothing filter. So in our work, first we perform the edge-aware smoothing operation on the reconstructed output T prime LAB and target image TLAB with guide image TL to get the smoothen output from here, which is FGS T prime LAB and TL, and get another smoothen output FGS TLAB and TL, and then we add the differences between these two filtered output to the target image TLAB to get the final color image T prime LAB. And the images for each one of these can also be seen here. And this is our final colored image. So after performing the color transfer with the help of guided image filters, we came across one more issue, and that was the color in some of our resulting images did not look quite natural, and some of the images lacked proper contrast, making the images appear to have more of a washed out effect. And also for some of the images, color was spilling out of the edges. We can also see that in this image right here. So to solve these issues, we used gamma correction. So specifically after obtaining the reconstructed image from deep image analogy, we performed gamma encoding on both target and the reconstructed image, where we used a gamma value of 1/2, and this was followed by the step that we performed in colorization using guided image filters, And then finally, we perform gamma decoding with gamma value of 2 to obtain the resulting colored image, which is T double prime LAB. And for both the gamma encoding and decoding, we basically perform the power law transform given by this equation. So we observe that with gamma correction, not only the color content spilling out of the edges was suppressed, but also the vividness of the image was improved to a certain extent, making the images look comparatively more sharp and detailed. An example of the result is shown in the figure here, where we can notice the difference in contrast and the difference in the amount of color that is being spilled out of the edges. So in addition to using fast global smoothing filter, we also perform the colorization operation with other guided image filters like guided filter, domain transform filter, weighted least square filter. Some of the previous research on these filters have shown that the fast global smoothing filter is not prone to halo effect, and it also provides speed advantage over other filters. So we chose to use the fast global smoothing filter in our colorization pipeline. Now we will move on to the reference image retrieval system. So for any reference-based color transfer task, it requires selection of good reference images. So to help in the selection of reference images, we propose to use a robust image retrieval system that automatically recommends the best reference image for performing color transfer. The figure here shows the complete pipeline of the reference image recommendation system. The inputs to the recommendation engine are the data set of our colored reference images and a single monochromatic image, which also acts as the query image. Ideally, the image suggested by the recommendation engine is expected to have similar semantic structure as the query image. We can see that the main recommendation engine block has two main components. One is the feature extractor, and another is the similarity matching block. So for feature extraction, we use the first fully connected layer of the VGG19 network. And for similarity matching, or basically to obtain the measure of semantic similarity between two images, we compute the cosine similarity. We use the similarity score to obtain the best reference image for performing color transfer. So these are the results that we obtained after part one. That is color transfer. On the second row, the first two images are two MRI scans of head, and the last one is a CT scan from the abdominal part. All of these images are basically grayscale images, and on the top row we have three reference images from where we need to extract colors and apply it to the grayscale images. On the last row we have the final colored images obtained after performing the reference-based color transfer. Now we will move on to the volume rendering part. So after obtaining the colored images, the second part was to render a 3D volume out of those colored MRI images. Currently, we are using a pre-existing volume rendering software that is 3D Slicer to perform the volume visualization. So we are using 3D Slicer to perform raycasting for direct volume rendering. And 3D Slicer is an open source medical computing platform. So let's see some of the results after the volume rendering. So this is the result for the volume visualization that was performed using 3D slicer for the top half of visible human head. In the first row, the volume is rendered with 33 monochromatic MRI images. And in the second row, we can see the colored volume, which was rendered with corresponding colored versions of those medical images. Uh, First column is the rendered volume. Second column shows the same volume from a different viewpoint. And the third column shows a cutaway view or a transverse section of the rendered volume. And similarly, these are the results for the visual human thorax and abdomen. For the volume shown in the first row, it was rendered with 328 monochromatic images, and the volume in the second row was rendered with the corresponding colored versions of those medical images. So these are some of the references that was used in this slide. And yeah, that's it from my side. Thank you all for listening. Thank you for being here.